Let's move on. So our next speaker is Malte Roentgen from University of Hamburg, Germany. And he's going to tell us about the compact localized state by local and latent symmetries. So let's welcome our speaker.
I think now you can hear me, right?
Yeah.
Sorry, I unmuted me. Yeah, thanks for the very kind introduction, and thanks again for organizing this beautiful workshop. Today I'm going to talk about some more basic ideas compared to the other topics, but I hope you will find it just as interesting and as exciting as I find it. Let me take this opportunity to thank all the people with whom I had the pleasure to work with on the projects. So first and foremost, this is of course my supervisor, Professor Peter Schmelcher, Christian Morphonius and Maxime Fisch, both working also at the University of Hamburg. And all works which I'm going to present today, I indeed have been done with those three people. I also will mention briefly some other works which I have been working together on with Professor Luca Dal Negro and Dr. Fabrizio Scrignoi from Boston University, Professor Fotis Diakonos and Dr. Nicholas Paleodimopoulos. So this name is always difficult for me to pronounce. He's now in Crete, but at that time he was in Athens. Yeah, and then let's start with the motivation. So this is, for me, by the way, Professor Flach, this was my first contact with flat bands, and I still highly like this paper. So this is the table which I grabbed from your paper, and it shows an overview over some well-known flat band systems. And when I saw it, I immediately caught my attention that those lattices here are full of symmetries. And then we started working on analyzing those symmetries, and our motivation and overarching question was like, well, given the high number of local symmetries, which role do they play for compact localization and flat bands? And then as a second point, can we use those symmetries in order to systematically construct such flat band systems? Before I continue, let me make another, which I think important remark. So in this week, we had many really interesting talks on different systems like magnons, interacting electrons, we had spin orbit interacting systems, and many other. The concept presented in this talk are in some way more basic in that they are independent of the system. And by independent of the system, I mean that I will not talk on the level of an Hamiltonian or even a normal operator, but instead I assume that you have chosen a particular basis. So for example, if you work in a Bose-Hubbard model, then I assume that you choose a particular filling when go to a specific basis. And then what you will end up with is, of course, a matrix, which is normally much bigger than this toy model system or toy model matrix, which I depicted here. It's just 4 by 4. And what I like about matrices is that you can always depict them as graphs. So this is shown on the left-hand side here. So we have got a 4 by 4 Hermitian matrix on the right-hand side. On the left, you can see that you can draw it as a graph with 4 vertices. And each line here corresponds to a non-vanishing matrix element of this matrix. And you might ask yourself, well, okay, why do I take this effort to go to specific basis? Because usually a second quantization language is more beautiful. And the answer is partly that it allows to see compact localization also in systems which you would normally not expect. So this is from a project together with Fabrizio Scrignoli and Luca Dal Negro from Boston. And so we investigated here a system of dipolar nanoparticles, which a small sketch of the system is depicted here in the inset. And these systems are open and they are described by a Green's matrix, not by a Hamiltonian. And now the interesting thing is, first of all, that each of those nanoparticles is modeled as a dipole. So it has 3 degrees of freedom, X, Y, and Z direction. And so the Green's matrix describing this setup is of dimension 12. But the same logic just for the Hamiltonian systems applies here as well, meaning that you can, well, draw this 12 by 12 matrix as a graph. And here, for example, each line corresponds to a non-vanishing matrix element. Sometimes the matrices for your Hamiltonian systems, I mean, they are much bigger and they are much more difficult to get anything from these drawings. But sometimes, just as well, I found that you can see many features and also local symmetries you can easily see from sketches. And indeed, in the graph theory community, there exists a large number of algorithms which try to visualize a large graph such that as a human being can immediately get or see the symmetries. Yeah, let me move on now for the topic. So first, I'm going to talk about local symmetries. So those are old results from 2018, and I'm not going to present them here to bore you, but rather to prepare you for the second and more important part of latent symmetries. So as you will see, the local symmetries are a good preparation for latent ones. So I have shown here, I mean, I think all of you know this, the diamond chain, which is of course a really famous toy model for flat bands. The band structure is shown on the left. You've got this prominent flat band at d equals 0. And why I'm showing you this is because this diamond chain has a very prominent reflection symmetry, which is here depicted as a gray dotted line. And of course, this symmetry is behind the compact localization, and I think it's easy to see. But let's just take one more minute to analyze this in a slightly more mathematical manner. So we have this reflection symmetry, and this implies that you can choose all eigenstates of this system to have definite parity. And of course, it's easy to see that the negative parity state will vanish on these central right sides. But we can also derive this in a mathematical manner. So if we take the negative parity eigenstate phi and compute the overlap with one of those right sides, then what we can do is we can use the fact that if you apply this reflection operation twice, you do nothing. So p squares to identity, and then you can insert it, act with 1p on the right side, which is just the identity because it lies on the axis of reflection. The other p acts on the phi, which is a negative parity eigenstate. And then if you compare those two terms, you immediately see that just as expected, or just as you know beforehand, that the negative parity eigenstate vanishes on this central line. Now, the important point is, though, that the state depicted here is not compactly localized. It's infinitely extended. And in order to explain the presence of a compact localized eigenstate, we need to go from a global reflection operation to a local one. And by local, I mean that we take a reflection operation which just acts in a single unit cell. So this is graphically depicted here. This operation here permutes those two sides and acts as the identity on all others. And of course, you can apply the same logic just as before and see that there will be a compact localized state. And since sometimes I even personally, I find it difficult to to visualize those, I prepared a small video which shows the difference between a global reflection operation and a local reflection operation here. Hope this video plays smooth also in other parts of the world. Not sure how the bandwidth is here, but as you can see, this global reflection operation and the local reflection operation, they leave the chain invariant. In other words, they commute with the underlying Hamiltonian. And that's the explanation for this compact localized state in flat band. Of course, you can also apply this logic to other more complicated lattices, for example, to the one-dimensional pyrochlore lattice, which has two flat bands, and the compact localized states are again localized in a single unit cell. So if I may show you another video, this operation is shown here. So as you can see, after the operation, the system looks just as before. And so this implies, or this is equivalent to the fact that this reflection operation commutes with the Hamiltonian. In case you wonder, yes, there are of course also non-commuting operations. And just to show you a basic one, so if we just take this reflection operation on a single dimer of these two sides, then you see after this operation here, the couplings cross, while beforehand they looked like this. So in other words, this operation here does not commute with the Hamiltonian. Well, instead of just using local symmetries to understand flat bands, you can also use them to design them. So this is depicted here. You got a very simple one-dimensional chain with two sides in the unit cell. It has two dispersive bands. And then if you apply the same concept, but just backwards, you can symmetrize this side. Here you get this dimer structure. If you also rescale the coupling, you see that you get the dispersive bands just as before, but additionally also a flat band. And it's not shown here, but if you change this on-site potential of those two dimer sides and additionally also connect them with coupling, then you can freely tune the energetical position of the flat band as you want. The mathematical basis of this is the so-called equitable partition theorem from graph theory. The paper is cited here. As you see, it's not done by us. It's done by a group around Benjamin Webb. And in layman's terms, I would say that the equitable partition theorem is nothing else but group theory, but it's a tool which allows you to forget about all these complicated terms like irreducible representations or character tables. It just gives you a simple algorithmic perspective on how you can use symmetries to block diagonalize a given Hamiltonian. And this is the principle behind all of this. Yeah, today the focus is more or less on latent symmetries. So if you're interested in more information, and of course you can generalize this concept to more than just reflection symmetries. Yeah, please look into this paper. As I said, it's already a little old, but I think the results are still interesting. Now I move on to the second part of my talk, and the by far most important, I think, at least in this context here. I will present it in a historical order, and meaning that we initially investigated latent symmetries not from the perspective of compact localization and flat bands, and I will show you just in this order. So please, for a moment, forget about compact localization and flat bands and just try to dive into the world of latent symmetries together with me. And so in order to introduce this concept, let me show you two very simple systems. So on the left-hand side, it's a four-side toy model. We've got a reflection symmetry. And well, as you immediately see, the eigenstates of this four-side Hamiltonian will have definite parity on the two red sides U and V. This is everything basic. It's even embarrassing to show it. But on the right-hand side, things get more complicated. So again, we have like a very simple system, 9 sides. And if you look sharply, you will see that it has no geometrical symmetry at all. And thus, at first glance, you might say, oh, well, this is an asymmetric system. But if you take the cost or the time and diagonalizing this system, then you will see that counterintuitively, the two red sides here, U and V, all eigenstates have definite parity on those. But there is no symmetry, which you can see. Explaining this local parity. So in a sense, this is parity without symmetry, but this statement is of course not entirely true because it's only on first glance that you don't see a symmetry. There's indeed a hidden, or as they call it, latent symmetry behind this parity. And let me explain what I mean by this term on the next slide. So a latent symmetry is a symmetry which is normally not visible directly in the original Hamiltonian, but which can be made visible through a graph theoretical method, which is a so-called isospectral reduction. And well, it's in graph theory, but it existed for a long time, of course, in physics. And for a physicist, it's nothing else but an effective Hamiltonian obtained by subsystem partitioning. So the idea is that you partition your original system into two parts, namely S and S bar. So S is a set of sides. For example, we take here S to be the two red sides, U and V. This is our subsystem S. And S bar is the complement, all other sides, which in this example here means all gray sides here. Then if we perform this isospectral reduction over these two sides U and V, what we get is, of course, 2x2 matrix, which with energy dependent entries. This is because we have an effective Hamiltonian. And important here is that this 2 by 2 matrix has a specific structure. Namely, if you draw it as a graph, then you immediately see that it's symmetric. It has a reflection symmetry. And this explains the term latent symmetry. So latent is something which is well, hidden in some sense. And this is as it is here. You see no symmetry here, but here afterwards you see it. And important, and the explanation for this interesting finding of parity without symmetry is that if two sides of a Hamiltonian are latently symmetric, this implies local parity. And by the way, before I forget, everything what I show you here is just done for real symmetric Hamiltonians, but it can be also generalized to complex or Hermitian valued Hamiltonians. Yeah, well, this is, now we have understood where this parity comes from. Now let's move slowly into the direction of compact localization. And indeed, I mean, I have designed this example system here with such that it features two compact localized states, which have 0 amplitudes on the 3 right sides, 3, 4, and 5. But before we see this, let me give you yet another piece of theory. So it turns out if you have a latent symmetry of two sides, as we have here, then it can be mathematically proven that there exists an orthogonal matrix, which we call normally Q. This matrix has eigenvalues plus and minus 1. It commutes with the Hamiltonian and it squares to unity. And this matrix has a very particular structure. So it acts as the permutation on the two latently symmetric sides U and V. So this is colored here. It sometimes, and this is now, I did it, I wanted this system to be like this. So sometimes it can act as the identity on some sides, which in this example here are the 3 right sides, 3, 4, and 5. So it acts as the identity on those. And now comes the interesting part that on the remaining side, which are here colored gray, 6, 7, 8, and 9, this Q matrix acts in general as an orthogonal operation. So I personally have no idea how you could visualize the action of this matrix in a low dimensional space. Of course, you can interpret this Q matrix as a high dimensional orthogonal transformation, but then at the end, we as human beings, we are only used to thinking up to 3 dimensions. So I personally have no idea how you can visualize this operation. If you have an idea, please let me know. I would be highly excited about this. And now just to contrast this latent symmetry and the corresponding Q matrix, let's go back to a normal reflection symmetry. So in this toy model case, there's exists permutation matrix. And just to remind you, permutation matrix is a matrix where in each row and each column, there's exactly one entry with a 1 and all other entries vanish. So this matrix here acts as a permutation on these two wet sides 1 and 2 and acts as the identity on those other sides. And well, as before, we have already seen how this acting as the identity led to compact localization, and we can repeat this game now for the Q matrix. So, well, if we do this game now, first of all, again, to remind you, due to latent symmetry, all eigenstates of the system have definite parity. And of course, there's at least one negative parity eigenstate, which I will call phi. And now we can, as I said, repeat the same game. So we compute the overlap of phi with the right side W. We then use the fact that Q squares to 1, insert it here, let 1Q act on the right side, which acts as the identity, 1Q on the eigenstate phi, which is a negative parity eigenstate. We compare those two terms and we see that this negative parity eigenstate vanishes on the right sides. So of course, this is not yet a lattice, but you might still call it compact localized on all but the 3 central sides here. So if we want to use latent symmetries and these right sides as a means for designing compact localization and flat bands, then of course it's important to understand why Q acts as the identity on the right sides in the first place. And it turns out that there's a simple mathematical explanation which reads as follows. So the matrix Q acts as the identity on a side if and only if this matrix valued equation here is valid. So h to the power k, u, v, uw, this matrix element here, and u and v are the latently symmetric sides. W is one of those white sides here. So this expression is equal to the same expression if you replace u by the other latently symmetric side v. In our nomenclature, I mean, in our works, we say that the white sides are singlets, and singlets because you can generalize these equations. So you can put more summands on those sides, and then you get what we call multiplets. We don't need to go into detail, but just know that you can expand this concept a lot. And now, and Professor Tasaki, I really enjoyed your talk because there were many slides where you depicted some random walks, and so probably for you it's well known, but for me it was a new insight, which of course has been known in spectrograph theory for a long time, namely that you can interpret any matrix power in terms of walks. And well, it can be generalized, but let's just focus on a very simple case where you have a Hamiltonian whose matrix elements are either 0 or 1. And then the statement reads as follows. The matrix element h to the power k, ij, gives the number of different walks of length k from I to j. And to visualize this maybe not so clear statement, we can look at the figure here. So for example, this is h to the power 2. So from the above statement, we see that the entries of this matrix are somehow related to walks of length k equal to 2. And the matrix element 1, 1 states that we have to count all walks which start at vertex 1 or side 1 and which end again at this side. So there are 2 of them. Well, you can go from side 1 to side 2, and then you have to go back because you have to end at side 1 as well. You can also go from 1 to 3 and back, and those 2 are the only possible options, and that's why here you get in the corresponding matrix element equal to 2. This can be done in arbitrary matrix powers, and it's I find it a really interesting way to to introduce the concept of walks through matrices. And now if we use this new knowledge and analyze this singlet expression, which is printed again for your convenience here, we see that the number of walks of each length k from u to w, the right side, is equal to the number of walks from v to w. So now we get a walk interpretation of this of why we have compact localization on those right sides. And I personally, the more I think about those walks, or the more I work with them, the more I see that they are really a source of deep knowledge about your Hamiltonian. And just to give you, so to say, the tip of the iceberg, let me give you an additional statement. So it turns out if 2 sides u and v are latently symmetric, as we had it before, this is equivalent to another matrix power equation, namely this one here. So h to the power k uu equal to h to the power k vv, which means in our walk interpretation, the number of walks from u to itself are the same as from v to itself in all matrix powers. And now to demonstrate how easily you can get into spectrograph theory and to interdisciplinary research, it turns out further that this condition, which is equivalent to latent symmetry, is equivalent to a statement about the eigenvalue spectra of the system. So the statement reads as follows. If you have this equation here, then you can start from your original Hamiltonian, remove the first latently symmetric side u, you get this h minus u graph or matrix. You can do the same with v, you get this h minus v. And then due to equation 4, you immediately get, or you can prove, that the eigenvalue spectra of those two different graphs here, they are equivalent, or they're not equivalent, they are identical. And this I find really interesting. I mean, you get from such a matrix power equality two statements about the eigenvalue spectra. And personally, I'm really curious whether if we study this, I mean, these matrix power relations further, what else we can learn about our Hamiltonians. Yeah, two more points on latent symmetries. The first is, as you have seen, not each latent, I mean, there are latent symmetries which are not reflection symmetries, but the reverse statement is true. So if you have a reflection symmetry, then you can show that it is a latent symmetry. And this implies that latent symmetry is in some sense a generalization of reflection symmetries. And when I personally think about symmetries, I always think about degeneracies. And in case you wonder, yes, it can be proven, and we have recently done it, that if you have a Hamiltonian with non-abelian latent symmetries, then it automatically features degenerate eigenvalues. Now let's come to the very last button. By the way, let me see if I can get, how many minutes more do I have?
You have about 15 minutes, including discussion. So 5 minutes per talk.
Okay. Yeah, thanks. That will be enough. Okay. Well, if we have a reflection symmetric system like this, then I think all of you know that if you connect a subnetwork to sites on which the compact localized states vanish, then the compact localization is not changed by this connection. And if previously, as I have said, reflection symmetry is also a kind of latent symmetry, and it turns out those sites on which this compact localized state vanishes are also singlets. And if you have this in mind, then you can immediately understand what is shown below here. So if you have a latent symmetry, you have those three white singlet sites, then you can just as well connect an arbitrary network, no matter how big, to the singlets. And the latent symmetry will not be broken. And all these new connected sites are also singlets, which means this gives us readily a building or construction principle. So we can start by picking a network with latent symmetries. And well, you can ask me also in the question round, but just to say there are plenty of those. And each day we find more. Then if necessary, you can equip this network with singlets. And interestingly, the procedure for doing this is a little bit technical, but again, it's based completely on an analysis of the matrix powers of the Hamiltonian, which again, yeah, it seems like the matrix powers tell you a lot about the Hamiltonian. This becomes more and more clear the more I work with those. And then you can use this network as a unit cell by connecting it through others by singlets. So this is shown for this example setup, which I showed before. We have this network here. We had latent symmetry of U and V. We had these three singlet sites on which the compact localized states vanish. And then we just built it into a lattice. And what you can see here is you get a lattice structure with three flat bands. And the two red ones are indeed completely induced and explained by latent symmetries. This principle can also be done in two-dimensional systems. And so this is like another example Hamiltonian with latently symmetric sites 1 and 2. It already has two singlets, 7 and 8. And then by analyzing the matrix powers, you can induce additional singlets. And the easiest way to do is just to connect a new site symmetrically to the two latently symmetric sites 1 and 2. So this singlet 9 here, if you think about it, then in the singlet condition, you will immediately see why this site 9 will be a singlet. And so this was step 2 of the algorithm before, and now we go to step 3, namely we embed this into a lattice. So we build a two-dimensional lattice and connect the unit cells via those singlets. You get the lattice here on the right-hand side. On the left, you see the band structure, and as we expect, there are actually two flat bands to those latent symmetries. Yeah, now this will take more 1 or 2 minutes probably. The interesting thing about latent symmetries is that you can normally parameterize the Hamiltonian. So this is shown here. This is the unit cell which we had on the slide beforehand, and now those different colors and P's mean that you can change those parameters, those coupling parameters here, without breaking the co-spectrum, I mean the latent symmetry, or breaking the singlet structure, meaning that you can really change all of those parameters and thereby change your band structure without taking away flat bands. And this is just two examples. So here we take a specific parametrization. We just parameterize those couplings here, where we the parameter P. And what is shown here is really compressed. And Christian Morphonis, by the way, he's a really master of compressing a lot of knowledge into beautiful plots. So what is shown here is the bandwidth. I mean, for each value of P, you get a band structure. And what is shown here is not the band structure itself, but just the bandwidth. So for example, at P equals 0, there's a dispersive band which varies between this value of just a little bit above 3 and up to here. And in this logic, of course, a flat band is a band with 0 bandwidth, and that's why a flat band appears as a single point. And since we vary the parameter P, you see that this flat band occurs at different energies, but there are always two flat bands, the two red lines. So you can change, I mean, the position of the flat bands. On the right-hand side, there's another parametrization. And there you can see that for each value of P, the flat bands stay at the energetic position, but the dispersive bands can be changed. Yeah, I'm nearly done. If you're interested in further information, because this is just the tip of the iceberg, we published 2 papers on this. The first is the underlying mathematical theory. It appeared in a purely, well, not purely, but a mathematical journal. And there we also show some means of constructing such latently symmetric Hamiltonians. And the second one, which, by the way, is done mostly by Christian Morphonis, so I'm just the presenter, I'm not the original author here, at least not the first author. This is, has been done, published in PRB. Yeah, and then a quick outlook. Well, the question is, of course, how many different networks we can, or how many different flat bands we can explain. And if we take again here this, by the way, the source is missing. Sorry, Professor Flach. So if we take this picture from your 2014 paper, we see that you can we can explain the 3 uppermost flat band systems, but unfortunately not the ones on the second row here. And which is also interesting to me is that there's this flat band classification in terms of how many unit cells do the compact localized states comprise. And until now, it seems that those latent and local symmetries will almost always only work on the U equal 1 case. But we are heavily working on generalizations, so stay tuned. And with this, I would like to thank you for your attention. And yeah, I'm welcoming your questions.
Thank you very much. Yeah. Thank you very much for the very interesting, clear talk. So now talk is open for the question. So yeah. So Rudolf, please go ahead. Yeah.
So I'm not sure. Can you see me? Can you hear me?
Yes.
Excellent. Thank you, Malte, for a really lovely talk. But the last slide now confused me when you said you can explain only sort of half of what's interesting, because I thought I understood what you're doing by basically saying you're sort of looking at the lattices and say those which I can in sort of physics speaks renormalize by putting these additional sites that you're having into sort of effective sites, as you showed very early on. Those sort of, then you can say, have the latent symmetry. But then when I look at the ones at the bottom of that slide, a particular, the one in the center of the bottom, I can certainly should be able to normalize those away, shouldn't I? And hence, why doesn't your stuff work there?
Well, the normalization, at least those sites are not latently symmetric. This we have checked. I think the problem is really that this state is extended over more than one unit cell. So, and we have some ideas, which is still a lot work in progress. Personally, I think that there will be another symmetry concept describing this. I mean, if first, as you also said, this looks highly symmetric. There should be something, but at least for this concept of commuting local symmetries, also with latent symmetries, we cannot yet explain this. But I don't understand the reason as of now. I just think that it is related to the fact that this compact localized state spans 2 unit cells. I'm not sure if this entirely answers your question.
Yeah, I'm not sure that my question has a simple answer. I was just trying to see if you're saying that out of hand, it doesn't make sense, but you're not saying it. So I think I understood something. I have a second question, if I can just butt in quickly, or maybe not, Alexei. Probably you go ahead, and I'll stop at the moment.
No, go ahead. I'll ask.
Alexei, please go ahead, Alexei.
Okay, well, actually, I mean, my question is heavily related to what Rudo was asking. Essentially mentioned that you cannot achieve this U bigger than 1 flat bands with commuting latent symmetries. What about non-commuting ones? That's one question, and I'll ask immediately the second question, because it's related. Did you consider perhaps did you study what happens if you reverse your procedure? So you start with the network that has clear symmetries, and then you apply this Q matrix. Like you make a reverse transformation, you see what happens, because this is also a way maybe to analyze the flat bands with U bigger than 1. You just try applying these transformations and you see what kind of lattices you would get, or graphs.
When you say apply this transformation, I mean, if your Hamiltonian already commutes with it, then nothing will be done. Do you mean that you start from a matrix of the Q matrix and then try to find the matrix which commutes with it?
Yeah, or perhaps if I consider that my flat band Hamiltonian is already a result of is a spectral reduction, and I try to see if I can find transformations that enlarge it in some sense. So
yeah, this is. Sorry to interrupt you. There's some delay.
Yeah.
Yeah, actually, Maxime Pisch, who is also has been working on both projects here, and he's also in the workshop. He's working on this idea. So starting with a specific latent symmetry expressed by some Q matrix, he investigates what kind of Hamiltonians do commute with such a matrix. And maybe, as you said, but we're not sure yet. As you know, we have a lot of ideas and we have some findings which somehow contradict each other. And we have the idea or let's say we have the hope of somehow unifying everything soon. But it seems that sometimes you can indeed construct such U higher than 1 flat bands with this.
Okay.
And then the first part of your question, sorry, I forgot.
Yeah, wait, I think you mentioned that, yeah, if I remember correctly, you mentioned that the U equal 1 flat bands you construct, so the symmetries typically commute with each other, the latent. So what happens if they don't?
Well, then if such a symmetry does not commute, you cannot make any statements in general. I mean, we have a theory on non-commuting local symmetries in terms of non-local currents, and I think Peter Schmelker did some lectures in South Korea some time ago on this. The problem is that as of now, we don't see how those non-local currents can help in designing or understanding flat band systems. But one more point, and maybe this has shown something. Well, if we think about symmetries, I mean, of course, the term symmetry is I don't say ill-defined, but it's highly ambiguous. So when people say symmetries, they normally mean in those lattice systems a symmetry which you can easily see by bare eye. But those latent symmetries or the Q matrix, as I've said, is a general orthogonal transformation, but it still is it is still a symmetry of the Hamiltonian in the sense that it commutes with H. So I personally have the hope that if we investigate more general orthogonal transformations, that those will explain those flat bands here. So in this sense, they are those. I mean, those will be commuting symmetries, but they will be not so geometrical local symmetries.
Okay. Okay. Yeah. Thank you.
Okay. So Ludolf, Rema, yeah, please go ahead.
Yeah, thank you. So if you go back to when you constructed those 2D examples, yeah, this so I have 2 questions there. A, can you also do it in 3D? And
Yes.
B, how much control do you have over them? I mean, it looks like you're just connecting basically points, and then the dispersive and the flat bands emerge. Can you engineer them? Can you decide that you want a flat band in the middle of a dispersive band, and hence you need to make the connection from A to B or something like that? Or is it just luck?
It is not just luck, but we are not yet, and I have to emphasize the yet, not yet at the point where we can completely control it. So,
but if I were to tell you I want something which has 3 flat bands and 7 dispersive bands, and I want 1 flat band in the middle of one of the dispersive bands, can you do it?
Not yet.
Thank
but
you.
I mean, to excuse my answer, let me emphasize that this whole study of latent symmetries is really new. So in the past 2 years, I mean, 2 years ago we started, and at that time we really, for the first time in my life, I saw the concept of walks, and we didn't understand at all why latent symmetry emerges. And then this thing was published, I mean, this year, but it was submitted last year. And then we are now at the point where we can really understand where a latent symmetry comes from, and we can already rudimentarily find some parametrizations. So I think if you give us, let's say, 1 to 3 more years, then probably we will be at the point where we can really design, as you said, yeah, 3 flat bands, 7 dispersive bands, and 1 flat band at that position. I think that's feasible. It's just that we did not have yet enough time to go into this.
Okay, thank you.
So, let me ask one very simple question. So you show the one example with the 3 flat band, and 2 of them can be explained by latent symmetry. One cannot.
Yeah.
What happened to the last one? Why you cannot explain by latent symmetry?
Well, I have not fully investigated it to the end, but at least, I mean, this unit cell here, it has 2, if you just look at the isolated without embedding it in the lattice, it has a latent symmetry, and it has 2 negative parity eigenstates. And those 2 correspond to those 2 flat bands. The third one, well, they are not, this third flat band here at E equals 0 is not related to those 2 eigenstates. And thus, if you go from the concept of latent symmetry and say you look at a single unit cell, then they cannot be explained. But well, it's on my to-do list to analyze it today in the evening, because here in Germany it's still morning. I cannot yet answer your question, I see. Sorry for that.
No problem. Okay, so the last question is Ludolf Rema again.
Sorry, I have another question. On the slide that you're on, when you construct your system, you always take basically then the same unit cell. But if you were to take different units, put them together, you would get rid of the dispersive bands, but would you still get flat bands? So don't make periodic copies, but you just, you know what I mean?
You mean like you construct an aperiodic sequence?
You construct sort of a random sequence, but it might still have flat bands, or would it not?
Well, you would, we would definitely, so just to rephrase it and to get sure what you mean. So you say, I take this thing as a first, not unit cell, but cell, then I put here something else, which has on the connecting sides latent, I mean, singlets.
Yeah.
Yes, well, if those other cells have the compact localized states as the same energy, you would still have macroscopic degeneracy. You will have not, so to say, traditional bands, and that you don't have any periodic symmetry, translation symmetry. But you will still get a macroscopic degeneracy. In this sense, well, there will be no band structure, but you will have the resemblance of a flat band.
But you will have the high degeneracy at
Yes.
these particular flat
Yeah.
band energies.
Yeah. So in this paper from 2018, we also had the idea, and I think meanwhile, I think I saw a paper on the archive. Some did this. That you have let's say one-dimensional system, which is not a lattice, and then you put those maybe not latently but local reflection symmetric units, and then you build like a quasi-crystal on top of this structure, and then you get like a an asymmetric, I mean, let's say an aperiodic system with a flat band, which also has properties of a quasi-crystal. So this you can also do, I think.
Thank you.
Okay, so I think it's time to move on. So yeah, let's thank Malte again for his very interesting talk. Thank you very much.